All right, lesson 7 is double angle identities. We're actually just going to flip right over. We're not going to worry about creating those identities. We're just going to know how to work with them because that's all you'll have to do on the diploma. So here are the double angle identities. What this means is sine 2a is 2 times sine A cos A, and then you can see cos 2a identities and tan 2a identities right there in the box. Okay, so what does this mean and how do we use it? Example number 1, prove that identity 2 tan x over 1 plus tan squared x equals sine 2x is valid, and state the non-permissible values. Okay, when it asks you to prove that it is valid, in other words, you're proving that it's an identity that is true for all possible values of x. Okay, so we're going to start with the left side, and our left side is 2 tan x. And remember, again, we always want to get rid of tan whenever we can. Now be careful, 2 tan x is not the same thing as tan 2a, okay? This means 2 times tan x, different than tan of 2 angles, okay? So we always want to get rid of tan wherever we can and write it in terms of sine over cos. So this means 2, oh boy, try that again. Must still have my highlighter on. So this is 2 times sine over cos. That's what tangent is. You can look on your formula sheet. It's one of your basic formulas. And that's all over 1 plus tan squared x. Well, 1 plus tan squared x, if you look on your formula sheet, is equivalent to secant squared x. Okay, when we have this, we know that secant squared x is actually 1 over cos squared x. So we're just going to rewrite this and actually multiply the numerator at the same time. So if I have 2 times sine x over cos x, that's the same thing as 2 over 1. So that's really 2 sine x
Mr. Truman, could you call the office,
over
please?
cos x on the numerator. And on the bottom, this is 1 over cos squared x. And we just got that off of our formula sheet. Now again, when I have a fraction divided by a fraction, I'm just going to multiply by the reciprocal. So 2 sine x over cos x times by cos squared x over 1, which is 2 sine x cos x. Oh yes, because my cos will cancel one of my coses here. And so in the numerator, I'm just left with 2 sine x cos x. All over 1, which I don't even have to write the 1. And once I've got it to that point, I can see that 2 sine x cos x is actually sine 2a, or sine 2x in this case. So that's equivalent to sine 2x. This is my left side, and now my left side is equal to my right side. As you do these proofs, kind of keep in mind what your goal is, what you're shooting for as you're going, because then when you get it to this point, you'll say, well, that doesn't look like I can simplify it any further, but I'm actually trying to get sine 2x, and then you'll go, oh, sine 2x, that's a double angle identity, and you can see, oh, that's 2 sine x cos x is sine 2x. And then you'll know how far to take it. So always kind of as you're simplifying and as you're working with these identities, always keep in mind what your goal is at the end and kind of work toward that, and that will help you a little bit too in the simplifying. Okay, now again, it says that we have to state the non-permissibles, and we learned about that in the last lesson. So that means we need to look for any tans, cotans, secant, and cosecants. Well, in this case, I do have some tans, okay? So I need to deal with those. And so I know tan is sine over cos. Okay, and so in order for this tan to be defined, means that my cos x cannot equal 0. And cos, let's just think about our cos function again. Cos would equal 0 where? It starts here, it goes like this, and this is 2 pi. So this would be pi. So this 0 here, it would be at 0 at pi over 2 and at 3 pi over 2. Okay? So in other words, x cannot be, we're going to take the first one, which is pi over 2, and we're going to keep adding multiples of pi. So some number of multiples of pi, where n is an element of integers. Okay, so this will be your final answer. Then we know that we also have to check for non-permissible values also in the denominator. Remember, this was step 1. We had to check in cotans, tans, cosecants, and secants. But then our second step is we have to check our denominators. Okay? Now, when we check the denominator, we do have a denominator, but it's 1 plus tan squared x. Okay? Is there ever any way that that tan squared x, 1 plus tan squared x, would ever equal 0? No, there isn't. Because if tan is squared, whatever number tan is, even if it's negative, once it's squared, it becomes positive. And then we're adding 1 to it. So it's always going to be positive. So there are no NPVs, non-permissible values, in the denominator. Okay? No restrictions. Another way that you might say it. Okay, class example number 2. Use the identity sine 2a equals 2 sine a cos a with a replaced by 3x to determine a double angle identity. Okay, so we want to come up with a double angle identity. That means, like we have up here in the boxes at the top of the page, the double angle identities, we want to come up with one of those. There we go, move it back up to where it was. We want to come up with one of those as our final answer, okay? A double angle identity for sine 6x. Okay, so we want to be able to say that sine 6x is sine 2 times something. That's what a double angle identity would be, okay? So think about that for a minute. Sine 6x would be the same thing as sine 2 times what? Well, obviously 3x, right? Okay, so that would be, if you look at the top of your page, I can't keep scrolling up and down because the scrolling feature is not working very well on this smartboard, but if you look at the top of your page or on your formula sheet, you can see that sine 2a, okay, so in this case, this is our a, is 2 sine a cos a. So what that really means is we'd be doing 2 sine 3x cos 3x. And I guess you could write it with or without the brackets. I guess I didn't really need to put those in. 3x cos x. 3x. Okay, so that actually would be considered a double angle identity for sine 6x. Okay, so we just divided out at 2. Okay, so we're going to do the same thing for b then. In b, we need to write a double angle identity for cos 10a. So obviously that's going to be cos 2 times 5a, right? And then again, since this is a double angle identity, this is our a, right? Okay, so if you look up at the top of your page, cos 2, a is either cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. Okay, so I'm just going to use the first one because I just have to write a double angle identity for this. So this would be the same thing as cos squared 5a minus sine squared 5a. That would be one double angle identity I could write for cos 10a. Okay? Now, tan x is a little more tricky because I need to figure out how I could write that as a double angle. So what I'm really saying is tan x would be tan of 2 times what? X.
Leroy Kalina to the office, please.
Yeah. 2 times half would be 1, right? So that's the same thing as tan x. Okay? So again, this is my A. And if you look at the top of your page, you will see that double angle identity is 2 tan A. So I've got 2 tan half x over 1 minus tan squared A. So tan squared half x. Okay, and that's how you'd leave it. All right, questions at the bottom of your page. I can get it to scroll. There we go. Okay, we've got 2 sine 4x cos 4x. This is sine 2 times 4x, isn't it? Okay, if you look up at the top of your page, 2 sine 4x cos 4x is the sine 2a for identity, isn't it? Sine of double angle A. And so what it's saying is that sine at 4x is your A. And so this is sine 2 of 4a, right? Okay, and then that is just the same thing as sine 8x. Okay, the next one, look carefully, we've got cos squared of something minus sine squared of something. If you look at the top of your page, you'll see cos squared A minus sine squared A. Okay, so our half A is our A in this case, right? So that is all equal to cos 2A. Cos 2A. And in this case, then my A is, these are my A's, right? So half A. And if you multiply that out, that's just cos A. Okay? And the last one, sine of something times cos of something. Well, that almost looks like sine 2a, but it's not, is it? What's missing? The 2 in front of that. So that's actually half of sine 2a. Okay, so what would sine 2a be? Sine 2a would be 2 sine 5 over 2x cos 5 over 2x. Okay, so that's half of well, 2 sine 5x cos 5x is sine 2a, right? Half of sine 2a. Well, what's our a? 2a. So that's half of sine of 10 over 2. So that's half of sine 5. Oh, and that should be an x in there, shouldn't it? I missed my x. So half of sine 5x. Okay, and the last thing we're going to look at just briefly, because I know this is a lot, is just on the very last lesson, lesson 8, where we're using identities to actually solve equations. And I think you'll see that a lot of this is review. It's not as much new stuff as the working with these identities has been. Okay. Okay, so lesson number 8, just really quickly. We've already learned how to solve simple trig equations, and more complex trig equations sometimes mean that you have to use what you know about the trig identities to substitute them in. And usually you have to express one equation in terms of...
Bailey Schwab to the office, please. Bailey.
You're going to express the equation in terms of one of the 3 primary trig functions, so in terms of sine, cosine, or tangent. Okay? Now, I just want you to make a note here. When an equation cannot be factored, you're going to find an identity to make them all sine or cosine. Okay? Usually not tan, usually sine and cosine. So just make yourself a note. When an equation cannot be factored, so try factoring it first. Find an identity. To make them all sine or cosine. Okay? And that's kind of what we've been doing all along. We have been changing our tans and substituting them for sine over cos. And so you're going to do that in this case as well. When an equation can't be factored, we will look for an identity that uses sine and cos. Okay? Okay, so the first one says, solve the following equations where our x is between 0 and 2 pi. Okay? So, first of all, we're going to look at this equation and we're going to ask ourselves first if anything can be factored. No, nothing can be factored. Okay, so now I'm going to look then to see if I can make them either all sines or all coses. Because right now, it kind of almost looks like a quadratic equation. It looks like something like this, x squared plus x equals 0, right? So I've got some x squared term, that's 2 cos, and I've got some regular x, there's 3 sine, okay? So but they're different. One is a cos and one is a sine, and I can't factor them or I can't work with them until they're all the same. So I'm going to look for an identity that will turn them either, I can substitute in that will make them either both sines or both coses, okay? Well, if you look for on your formula sheet, 2 cos squared x. Okay, no, there isn't anything that is 2 cos squared x, but I know something that is cos squared x. If you look just about a third of the way down your formula sheet, you see sine squared x plus cos squared x equals 1. Don't write this down. Okay. How would I rearrange this equation so that it would give me cos squared x? Cos squared x equals 1, and then I'd have to subtract sine squared x from both sides, right? And if I did that, then I would end up with what cos squared x is. And I can use that value to substitute in here for this cos squared x. Okay? So cos squared x is, I'm going 2 times what cos squared x is. And cos squared x is 1 minus sine squared x. And then I still have plus 3 sine x equals 0. Okay, because it is an equation, it's going to equal 0. Now I have them all sine. okay? It's much easier to work with when you have it all signed, okay? Because now I can actually solve the equation. So I'm going to multiply this 2 back into the equation by distributing it here, multiplying it by that and by that. So that gives me 2 minus 2 sine squared x plus 3 sine x equals 0. Now I need to rearrange this a little bit again because I want this equation to look like
Joanne Holder, if you're still here, could you come to the office, please?
x squared plus x plus 4 or whatever equals 0. I want my x squared term, then my x term, then my constant. So that it's in a format, it's in standard form, and I'll be able to factor it. Okay, so what that means is I will have negative 2 sine squared x plus 3 sine x plus 2 would go at the end then, wouldn't it? Okay. Now, again, I don't like this negative 2 in front, so I'm going to divide both sides by negative 1. And when I do that, it's going to get rid of that. And it's also going to change all of these signs because I'm dividing by negative 1 or multiplying by both sides by negative 1. Either one will work. Okay, so now I should be able to factor this. And this is just exactly the same as regular factoring. I see again, I have not just one sine squared x, but I've got 2 sine squared x. So remember, I have to use method of decomposition. So I'm looking for 2 numbers that will multiply to give me 2 times negative 2, negative 4, and those same 2 numbers that will add to give me negative 3. So the numbers I'm looking for are negative 4 and positive 1. All right, so this is going to be 2 sine squared x minus 4x plus 1x minus 2. Okay, then I'm going to take out a, oops, sorry, this, I forgot, this is not just 4x, it's 4 sine x plus 1 sine x minus 2 equals 0. Okay, now I'm going to take out a 2 sine x. Remember, I'm going to group those first 2 terms, those last 2 terms, keep my sign in the middle. So I've got 2 sine times, 2 sine x times sine x minus 2 plus 1 times sine x minus 2. Okay, so my factors will be 2 sine x plus 1, and my other factor is sine x minus 2. Okay. I'm going to go up here to finish this question. So now, like any function or expression that I've factored, and I have to set both sides equal to 0. So that means 2 sine x plus 1 equals 0, and sine x minus 2 equals 0. And so this will be 2 sine x equals negative 1, sine x equals negative 1 over 2, and this one sine x equals 2. Okay, now I need to look on my unit circle and see where sine is equal to negative 1/2. And if I look, I find that sine equals negative 1/2 at 7 pi over 6 and 11 pi over 6. And then I look on my unit circle to see where sine is 2, and sine never is 2. So this root has no solution. Okay, so that means the x's in this equation are 7 pi over 6 and 11 pi over 6. Okay. Okay, I'm going to erase all of this because I need space on this other side. we've got cos of x plus pi over 6 minus cos of x minus pi over 6 equals 1. Okay, so this is cos of a plus b minus cos of a minus b, right? Okay, so when I look at my formula sheet, I can see that that cos of a plus b is cos of a, cos b, minus sine a, sine b. Okay, so this is going to be a rather lengthy
Ms.
one.
Baker, could you call 201, please?
Okay, so according to the identity, this is cos x, so we've got, that would be cos x times cos b, which is cos pi over 6. And all of that, oops, I guess I don't need those brackets that I thought I needed those brackets, but I don't. Okay, then it's minus sine A sine B, so you're going minus sine X sine pi over 6. And that's just this part, okay? That's just what cos A plus B is, okay? Now we need to look at what cos A minus B is. And if you look on your formula sheet, you can see that that's cos A, cos B plus sine A, sine B, okay? So all of that, that's where the bracket goes, minus all of this. We've got cos x, cos pi over 6, plus sine x, sine pi over 6, and that all equals 1. Okay, now here's where we're going to use what we know. Okay, so we're going to look on our formula sheet, or our unit circle, I mean. Obviously we can't find cos x on there, but we can find cos of pi over 6. That's cos of 30 degrees. Okay, and that is root 3 over 2. And then we still have this cos x that I've underlined in blue. Okay, minus, now sine of pi over 6 is a half times sine x. And then we're subtracting, okay, again, cos pi over 6 is root 3 over 2 times cos x. And then plus sine x, sine pi over 6 is a half times sine x equals 1. Okay, now, because I'm subtracting this whole part, I have to remember to distribute the negative sign to both terms, okay? So this will be root 3 over 2 cos x minus a half sine x minus root 3 over 2 cos x minus 1/2 sine x equals 1. Okay, now that doesn't look very nice. It looks a little nasty, but what I see is root 3 over 2 cos x minus root 3 over 2 cos x. Those two are going to cancel each other out. I've also got a negative 1/2 sine minus half sine. So that gives me negative a half minus a half is negative 2 halves, which is negative 1. So really we've just got negative 1 sine x equal to 1. Divide both sides or multiply both sides by negative 1 gives you sine of x is negative 1. And we can look on our unit circle to see where sine x is negative 1. And that is at 3 pi over 2. Okay, so that's the solution to the equation. Okay, so with these equations, you just factor them if you can. If you cannot factor it, then find an identity to make them all sines or all coses so that you can deal with it. And then you just use regular algebra to continue solving for x. Okay, and then use what you know. Use your unit circle to help you get them all equal, or to find out what the value is of x. Okay, we're going to try one more, and then I think that would be enough of an introduction to this for you. Okay, so this says consider the equation 4 minus 7 sine x equals cos 2x. And it says which of the three identities for cos 2x would be the most efficient replacement for solving this equation. Okay, this is kind of like the question we had a minute ago, where we looked up to the top of our page and we saw that, yes, there are identities for cos 2x, but there are three of them. How do you know which one to use? Well, you use the one that would make the most sense in the situation. Okay, so for instance, if I'm trying to solve 4 minus sine x, then I'm going to use the one that has, that doesn't have any coses in it, because I want to get them all sines or all coses, right? So I'm substituting this for something that's going to have sines in it, but I don't want to introduce coses into it or I won't be able to solve. Okay, so you just try and find the one that would make the most sense. And since this is 4 minus 7 sine x, I want the cos 2x identity that's going to have sine in it, but no coses. So that's the third one. Okay, so the one that would make the most sense would be cos 2x equals 1 minus 2 sine squared x. Okay, so it wants us to determine the general solution. That means for any value of x, okay, and for solving this. Okay, so let's write that equation down. 4 minus 7 sine x equals cos 2x. Okay, now we're going to use this identity that we've just identified in A to replace this part. Okay, so 4 minus 7 sine x equals 1 minus 2 sine squared x. Okay, now again, because this is an equation and I'm trying to solve for x, I need to get all of my x's and constant terms on one side, and I need a 0 on the other side. Okay, now since this is a negative 2 sine squared x, I'm going to add 2 sine squared x to both sides. Okay, then I've got minus 7 sine x, and then I'm going to subtract a 1 from this side and subtract a 1 from that side, so that's going to be plus 3 equals 0. Okay, now I can solve it. 2 sine squared x, in order to factor this, because I don't have just a single sine squared x, I've got 2 sine squared x, I have to use method of decomposition again. So I'm looking for two numbers that will multiply to give me 2 times 3, so 6, and two numbers that will add together to give me negative 7. So I'm going to use negative 6 and negative 1. Okay, so we've got 2 sine squared x minus 6 sine x plus, minus 1 x sine x plus 3 equals 0. Okay, then remember I grouped my first two together, I grouped my last two together, and then I'm going to factor out any common factors. I see a 2 sine x in both, so that would leave me with 1 sine x minus 3, and then I have minus 1 sine x minus 3. As long as this term is the same as this term, I know that I've done it correctly. Now I'm going to group what's outside of the brackets together. 2 sine x minus 1 is one factor, and sine x minus 3 is the other factor. Okay, Then continuing on as we always have, we set both factors equal to 0. So we've got 2 sine x minus 1 equals 0, and we have sine x minus 3 equal to 0. This would be sine x, 2 sine x equals positive 1, so sine x equals 1/2. And this one would be sine x equals 3. All right, so again, we're going to look on our unit circle and see where sine x equals 1/2. And sine x equals 1/2 at pi over 6 and at 5 pi over 6. And sine x never, never, never does become 3, and so there's no solution on this side. Okay, now we haven't quite answered the question because it asked us for the general solution. Okay, so remember we're going to take our pi over 6 and we're going to add some number of 2 pi. And we're also going to do the same for the other term, 5 pi over 6. Where our n is integers. In other words, we're adding or subtracting complete periods to get each of the values of x. Okay, so that would be your general solution. All right, so I think that gives you enough of an understanding of how to solve equations. It's just like regular algebra, except that we're using sines and cosines. Just remember that you want to get all of your variables really the same. And so if you have sines and coses in the same question, you're going to want them either both sines or both coses. And you're going to use identities to substitute like we did here to get, instead of having a sine and a cos, we needed to get this into a sine, right? So that we have sine and sine, okay? And once you do that, then you just solve it using regular algebra, solve for x. Find your roots of the equation.